Hey guys, as my last video was way too long, so I splitted that video and this particular video solely focus on WebAssembly.memory. Let's move on. Let's try to understand memory now. So in order to understand memory, let's step back a bit and try to understand how applications work on your machines. So now, whenever you are running a particular executable, that executable is first loaded inside the RAM, which means all your variables, functions, classes, objects that you have declared and used, all those are allocated memory. And then that memory is part of your RAM. Once all those portions are declared, initialized, memory has been provided to them, then your application starts. The same way, WASM file also requires memory to run on your machine or on your web application. That memory is provided by WebAssembly.memory module. WebAssembly.memory module acts as a bridge between a WASM file's code and your machine's RAM. Let's see how it works now. So WebAssembly.memory is nothing but an encapsulation over array buffer, which means it's quite similar to it. In what ways? In simple ways that memory is a linear array where each block represents 1 byte data, similar to array buffer. But there is one difference as well. We can instantiate array buffer providing the number of bytes that it requires. So let's say we created a new array buffer providing 10 bytes. So it will create 10 blocks of data, each block representing 1 byte. But memory doesn't work that way. So the way memory works inside WebAssembly module is that it says, hey, don't give me just a random number, the way that you provide array buffer its size. What I need is a page size. So what does page size mean? A page size is equivalent to 64 kilobytes of data. So whenever you are initializing a memory, providing it a page size of 1, it will internally create an array buffer with a size of 65,536 bytes, which means an array buffer with the size of 64 kilobytes. In that sense, WebAssembly.memory and array buffer are different. Now, if you grow your memory twice, what it will do is that it will internally increase the size of array buffer 2 times. Now, the size of array buffer would be 128 kilobytes. Let's see it in action now. So let's explore the memory object now. So the memory object has 0 page size and its array buffer that it encapsulates also has 0 byte length. Let's increase it a bit. So we'll reinitialize memory and this time I'll provide 1 as the initial value, which means that it has a page size of 64 kilobytes. So if I see memory now, it says, okay, it's of page size 1, but the array buffer has 64 KB length inside it. So 65536, and if we divide it by 1024, will give you 64, which means 64 kilobytes. And if I increase it more, let's say I reinitialized it with 2, this time the memory has page size of 2 and array buffer is actually double now. So if I divide it by 2, the number 65536 or by 1024, 128 kilobytes. So this is how memory increases in batches of 64 kilobytes. And there's another method that we have in memory, which is grow. So we can increase its page size by 1 by passing in the integer 1. And if I press enter, so its size has increased. Now it's triple, like it's 192 kilobytes now. So 199,608, sorry, 6608, single 9, 1024, 192 kilobytes. So this is how memory works, and this is how it encapsulates buffer, array buffer, and this is the root difference between memory and array buffer. Let's move on to the next section now. So let's explore the memory object now. So the memory object has 0 page size and its array buffer that it encapsulates also has 0 byte length. Let's increase it a bit. So we'll reinitialize memory and this time I'll provide 1 as the initial value, which means that it has a page size of 64 kilobytes. So if I see memory now, it says, okay, it's of page size 1, but the array buffer has 64 KB length inside it. So 65536, and if we divide it by 1024, will give you 64, which means 64 kilobytes. And if I increase it more, let's say I reinitialized it with 2, this time the memory has page size of 2 and array buffer is actually double now. So if I divide it by 2, the number 65536 or by 1024, 128 kilobytes. So this is how memory increases in batches of 64 kilobytes. And there's another method that we have in memory, which is grow. So we can increase its page size by 1 by passing in the integer 1. And if I press enter, so its size has increased. Now it's triple, like it's 192 kilobytes now. So 199,608, sorry, 6608, single 9, 1024, 192 kilobytes. So this is how memory works, and this is how it encapsulates buffer, array buffer. So let's also take a look at what is maximum. I'll clear the console and I'll declare a WebAssembly memory again, and this time I'll pass initial as 0 and maximum as 2. So memory is 0. Now if I grow it by 1 page size, its size is 64 KB. Now if I grow it once more, it will become double now, and now its size would be the double, like 128 KB. But now if I try to increase it by one more time, it will throw an error. Reason being that we've provided maximum limitation here. So it says maximum memory size exceeded because the maximum size is 128 KB. So this is how you can put the limitation on memory size as well. Now since we have done all that starting stuff, understanding memory and how it encapsulates array buffer, let's just focus on how assembly script manages it internally. So I've created this small snippet where I'm exporting a function called getArray, and I'm also providing a size to it, and it returns me an int8 array. Okay, so I'll generate a WASM file and then I'll try to load it. So you see the exports object provides me two things, getArray and memory, and you see memory is of 1 page size and array buffer has size of 64 kilobytes. Now let's just call this getArray method. So this getArray method would return me an array, and to be precise, it will return me the index where this array is stored inside the memory. So I created an array of size 10. So the int8 array would be using 80 bytes. Now you can see the array buffer has 64 kilobytes of size. How about we try to overflow that particular memory and see how assembly script's WASM file handles it. So I'll do 1000, and we'll also see what's the status of memory. So it says its page size is still 1, which is fine. So that means that the array that we declared has not overflown the memory yet. So I'll increase it to 10,000, and now again it's 1. Let's increase it a bit more. Let's say 50,000 now, and this time you see the memory increased on its own, because at some point of time during the initialization of the array, the index went out of bounds of the memory, and the memory automatically increased its page size. So this is how if we don't put a lid on the maximum memory that can be used, it just automatically increases its size, which is actually not correct, if you see, because there can be memory leakage in our programs. So let's see how we can put a tab on it using assembly scripts compiler. So now to put a tab on the maximum memory that can be used by our WASM file, assembly script has provided us a flag called maximum memory. So I'll provide it a value of 1. So whenever we increase the size of the array that we are generating using the getArray method, it'll throw an error if it gets out of bounds of the memory. So I created this WASM file and let's load it. So I got the memory again, and this time I'll just increase it to 50,000 straight away, and we get an error called unreachable. So this unreachable runtime error means that we are trying to increase the memory, but since we've already put a limit on it, which is 64 kilobyte itself, it threw an error called unreachable. We can see here this getArray method is trying to call function 9, and this function 9 actually tries to increase the memory by calling memory.grow, but then since it is not allowed, it throws an unreachable error. And this is how the memory is managed from the assembly script side. So this is how assembly script manages memory internally. If we provide a lid on it, it throws an error called unreachable. If we don't, it just grows dynamically. But assembly script has also given us a provision where the web application in itself can provide the memory so that it can take a hold of how the WASM file works on the web applications. So assembly script compiler has provided us a flag called import memory, which tells the web application that while instantiating the WebAssembly module, you need to provide a memory object as well. So let's try that now. And if I load the WASM file, it throws an error. So it says that the module and env should have a function called memory. I mean, it needs an object called memory, and let's see how to add that. So I'll create a memory the same way that we saw in the previous example, memory, and it needs a descriptor, and I can provide the initial to be 0, and let's just provide it memory, and let's load it now. Now it says the memory import 1 is smaller than the initial. Reason being that if you remember, during the compilation of our WASM file, assembly script implicitly gave memory size of 1, which means that while declaring the array and all that stuff, assembly script internally requires at least 64 KB of page size. So we need to provide it so that the WASM file can load and run. So we'll provide 1 here. And let's load it again. Now you see we have received the WASM file and it's got compiled correctly. We can also test out the same thing that we did. We'll just keep a check on memory, and then let's just call getArray 50,000, and this time temp1's memory has increased automatically to 2. So again, we can put a tab on it, and we can simply put a tab on it by providing the maximum as well. So let it be 2, and then load it again, store, and this time I'll call it, and the memory would have been increased. But now if I call it again with an increased number, let's say 80,000 or so, this time it's fine. Let's do 90,000. This time also it's fine. Let's do 1K, but this time it threw an unreachable error. Reason being that it could not grow the memory beyond 2 page sizes, which is 128 kilobytes. And if we see temp1, the memory is still 2. So this is how we can inject memory, and we can put a lid on it, or we can create it dynamically. It's better to put a lid on it, reason being that if there is a memory leakage, we can identify that. Instead, it'll just keep on consuming RAM. So let's move on to the next section now. So while evaluating memory, I found out that assembly script uses around 36 kilobytes of data internally, and the rest of the memory can be used by other initializations. So that is why when we were trying to declare an indent array here inside it, its size can only be increased by 28,652, which is actually in the range of 64 kilobytes. So if the number increases by one, just one, so this becomes 68,28652 to 28653, the page size of memory would increase by one more dynamically. So it'll turn to 128 kilobytes. So let's see it in action now. I'll load this WASM file, so it has variable, and I'll call get array, and I'll pass the magic number here, which is 28652. And if we see temp1, the memory still has 64 kilobytes of page size. Now if I just increase this number by one more and see the temp1 again, the page size has increased because it overflowed the actual memory that was there. Now since rest of the page size, the 64 kilobyte that is added, is free to us, we can actually create a new array with 64 kilobytes plus the size that is around 28 kilobytes here. So 64 kilobytes turn out to be 65,536, and we can add 28,652 to it. So until this number, our memory will not throw an error because it'll be in the range of two page sizes. So it's fine, it didn't throw an error, and memory size is still 2. As soon as I now increase this number by 1, it'll throw the unreachable error, as you can see now. So this is how memory is managed internally. We'll see how array stores its value inside the memory, and then we would be done with this particular video. So just to demonstrate how array works, I'll edit this code a bit, and instead of I32, I'll take in I8 size, and I'll also take a number which would be of I8, and what I'll do is that I'll add the multiplication inside the array itself. So for loop index of I8 type should be less than size, that's it. And the array would have I plus 1 and return I8A. Okay, so what this function does is that it creates a new int array, and then it stores the multiplication of the number that we are passing times the size. So let's output this file and run it. So I'll load the WASM file. I've got the array. I'll store this as global variable, and temp1.get array, pass in, let's say 20 and then 3. So I received 36016. So what is this 36016? 36016 is the index of the array buffer present inside the memory from where the initialization of the int array starts. So what happens is that whenever you declare an array, the initial 32 bytes are stored for extra information, and the data starts after those 32 bytes. So the actual data would be found at 36016 plus 32. So at this particular address. So if I store this int array as a global variable, temp2, I'll pass in 36048. So you say it gives us 3, and if I move forward to 9, it gives us 6, 50, it gives us 9, and so on. So let me just open this particular area, 36046, 36048. Okay, so 36048, 4, 8, and here it's the multiplication table of 3. So 3 till 20, and this is how the array buffer or indate array, whatever we are declaring inside the assembly script code, is stored inside the memory. Let's see how int32 array behaves and how it uses the memory. What I'll do is that I'll just change this indate array to int32 array, and the return type should be 32, and that's it. So let's just build this WASM file and load it in our application. And I'll simply initialize the array data, passing in 20 and 3, and it gave us this address back. So 36016 is the address where our array starts, and initial 32 bytes are being used by the address of the array and its internal handling, and from there onwards we will actually receive the correct data. So if I go to the memory and let me store indate array, and this time temp 2 and plus 32 gives 48, I get 3, which is fine. And if I go to the next address, it's 0. But why? Because in the previous section it was 6, but why is it 0 now? Reason being that in the previous section we declared an indate array, which means that a single entry represents 1 byte. But here we have declared int32 array, which means that a single entry inside the int32 array is actually of 4 bytes. So that is why if we are to get the second value, we need to add 4 after 36048. So it would be 5, 2, and then we got 6. And the next entry would be plus 4 again, which is 5, 6, and then we got 9. And you can see it inside this indate array. Let's go to this address again, 36048. Okay, so see, 36048 is 3, then we have 6 at 52, 9 at 56, 12 at 60, and so on. And we have to go till 60, and at 1 to 4 we have 60. So this is the difference between int32 array and indate array and how the values are stored inside the memory. If you want the values to be coagulated, you can open the int32 array as well, and inside int32 array I think the address would be 36048. I need to divide it by 4. It's 9012, and if I go to 9012 here, 9012, yep. So we have these values here attached together because this is a representation of, this representation is of int32 array of the array buffer. So we have these values bunched together. Now if I go to int16, the gap would not be 4, it would be 2. So instead of division by 4, I'll divide it by 2, and 18024 is the address here. So 18024, it's the wrong one. 18024. Okay, so here we have 3, and then at divisions of 2 we have different entries. So this is the representation of array buffer in int32, int16, and int8, and so on. And this is how memory works, and different variables are stored inside the memory.